Hi, and welcome to Allen High School's discussion of chemical bonding at the APIB HL1 level. We've been discussing covalent bonding and Lewis dot structures, and now we're going to begin to see how Lewis dot structures can lead us to a three-dimensional structure. And we're going to be doing two main models and eventually adding a third to that. The first is VSEPR, or valence shell electron pair repulsion. You should know what that acronym means. You should know each word in the acronym and what it is referencing. So first off, we're talking about the valence shell, those outer S and P electrons. And we're looking at how pairs of electrons repel one another in such a way that they dictate the three-dimensional geometry or structure. Now, that repulsion has a magnitude, or at least an ordering of magnitude. Certainly, a bonded pair will repel a bonded pair of an electron. What we find is that non-bonded pairs really like their personal space. They like to have a little bit more freedom of motion. They are not held so rigidly in place between two atoms, so they repel even more. So you get even greater repulsion. And then between two non-bonded pairs, you get the most repulsion. Okay? So that's what we're going to be looking at. And I'm going to text my son because he's about to come in and interrupt us here. So I'm going to interrupt us to keep my son from interrupting us. There we go. Okay. I hear, you know how I know? He pulled in the garage and I can hear his stereo going boom, boom, boom. I think you understand that as teenagers. Okay, let's recap. Non-bonded pairs repel non-bonded pairs the most. Non-bonded pair repels a bonded pair the second most. And then finally, bonded pairs repel bonded pairs. And so what we're going to find is that in a structure like an AB, like those are peripheral atoms, remember? That's why I was teaching you those. X, all right? What we're going to see is we're going to see repulsion between those electrons so that they will move in three-dimensional space to get as far away from one another as possible. So that's one of the models that we'll use, and we're going to build that and explore that. And don't let me forget to show you a little video clip in class, because it is so helpful on this. It does a far better job than I could ever hope to do. Okay, the second is hybridization, and we're going to be looking right now. This only deals with single bonds, all right? Hybridization deals only with single bonds, and I can spell single even. We will hold off our discussion for double bonds later on. So they're called, double bonds are called pi bonds. Hold that thought, all right? I'm going to go into more detail on that later. All right, let's look at hybridization. Hybridization is like a mathematical mixing of atomic orbitals to form molecular orbitals. Okay, so what it says is that for each molecular orbital that we need in a molecule, we're going to hybridize or mathematically, and this one's hilarious to watch on the video clip I'm going to show you, so definitely remind me to show you this. We're going to mathematically hybridize those. Now, organic chemistry is especially fond of this model, and so let's take a look at it. We have, let's say we need AB3X. Well, we need molecular orbital space. Let me draw it. In fact, let me draw that out a little better. We have A with the 3 B's. You can think of molecular orbital space as like an atomic orbital. An atomic orbital is a region in space where there's a 90% chance of finding an electron with given energy. Well, a molecular orbital would be a region in space where there's a 90% chance of finding the two electrons involved in a bond. So I need molecular orbital space for non-bonded pairs on the central. We are only counting what's on the central atom and then bonded electrons. So to find the number of molecular orbitals, you add B plus X in our ABX structure. So in this case, we have AB3X, B plus X would be 4. Okay? So if B plus X is 2, that means I need 2 molecular orbitals. Well, if I need 2 molecular orbitals, I'm going to hybridize or mathematically mix 2 atomic orbitals. So let's look at our atomic orbitals. We have 1 s orbital. We have 3 p orbitals. Now there's some controversy about the use of d orbitals. The most we would use are 2, and scientists, I'm going to go ahead and show you what it would be, but scientists have begun to view that model of hybridization, at least for these last 2. That's kind of losing favor in the scientific community. But definitely these you will see in organic chemistry on a regular basis. So if I need 2 atomic orbitals, I just take 2. So I'm going to need an S and I'm going to need a P. So it's S-P hybrid. Okay, well, let's see what I would have. I lost my little S. There's my S and my P. Okay, what if I needed 3? So if I need 3 there, okay, then I need 3 atomic orbitals. Wow, this is really not working very well for me. I'm sorry. So I would need to take 3. So you start with an S. You've only got 1 S. And then I need a P, and I need a P. 1, 2, 3 atomics. So we call that sp2 hybrid. What if I have 4? B plus X is 4. I need 4 molecular, so I take 4 atomic. And so I start with an S. I need a P, and a P, and a P. So 1, 2, 3, 4. This would be called sp3 hybridized. I think you see the trend here. Okay, to do 5, I need an S, a P, a P, a P. I'm out of P's. There's only 3 p orbitals available, so I've got to move into the D. So this would be called sp3d hybridized. You might see dsp3. Okay, this is in order of energy level, and this is in order of energy value. If I had 6, I'd need an S, a P, a P, a P. I'm all out of P's. Jump into the D's, and I'd need 2 D's. And this would be called sp3d2. You may see that written as D2sp3. Both are considered acceptable. Okay? Now, again, these latter 2, that explanation for the expanded octet, scientists alter models all the time. As new experiments are completed and new data is gathered, sometimes they alter it. And this is not thought to be a very good explanation for that expanded octet. But I'm going to go ahead and teach it because you may see it crop up until you get into college. Sometimes it takes a little while for these things to fully become embedded into the course. So I think it would be valuable for you to see it. All right, let's take a look at formic acid here. That's the sting of an ant bite. And it's got 1 central atom, A. I'm going to call that whole thing a B. Remember I said it could be a cluster of atoms hanging off as well. So A, B, 3. There are no non-bonded pairs on the central atom. There are non-bonded pairs on the oxygen atoms, but not on the central atom. So often what we'll do is in long molecules, you zero in on one atom and define it as the central atom. Okay, B plus X is equal to 3. So I need an S and a P and a P. So this is considered sp2 hybridized. We're going to be doing some work on this in class. I have an activity for that. And so until then, this is signing off.